By now, you should be familiar with the concept of the types of mechanical energy, kinetic energy, gravitational potential energy, and elastic potential energy. Now we're going to discuss the conservation of mechanical energy and use that to figure out different situations where we have an initial and a final mechanical energy of a system. So we know that the sum of both the kinetic and potential, and all types of potential is what I'm talking about here. Sometimes there's only gravitational, sometimes there's both gravitational potential energy and elastic potential energy. But the sum of all of that gives us the total mechanical energy for the system. Okay, an example that has both kinetic and potential energy at the same time would be a falling object, which we've talked about, and a roller coaster, which we're going to get into more in depth. Okay, on the right-hand side of my screen, you're going to see an example of a falling object. At the very top, the total mechanical energy is going to be all in one form. Because it's not yet moving, right? A falling or dropped object always starts at rest. So that means it's some height above the ground at Ymax. It has all gravitational potential energy and zero kinetic energy. Once the object starts to fall, then it's going to lose potential energy and gain kinetic energy, right? The potential energy has to go somewhere. It doesn't just magically disappear. At the halfway point, right, half of the height is going to be half potential and half kinetic. As the object continues to fall closer and closer to the zero level, or the y of 0 meters, the potential energy is going to continue to decrease and the kinetic energy is going to continue to increase to where it all converts from potential, which is why you see zero potential here, and all kinetic energy. Okay? In order to determine how much total energy the system has, the easy way to go about that is either finding the total potential, which would be using its maximum height, or finding its total kinetic using its maximum speed. Okay, the total height, or the maximum height, is at the top. The maximum speed would then be at the bottom. Okay, you're trying to look for where all of our energy is in one form, and that's why we either use the maximum height or the maximum speed. Okay. When talking about conservation of mechanical energy, we are talking about conservative forces, meaning we are disregarding air resistance and friction, because those things are going to take away energy from the system. Okay, just to give you some examples. Okay, some examples where an object will gain kinetic energy as it loses potential energy would be a falling object, right? As the height decreases, the speed is increasing. And we know that potential energy gravitational is dependent upon the height, and the kinetic energy is dependent upon the speed. We could also say something that is going downhill on a roller coaster or down a ramp, right? As it decreases in height, it will increase in speed. When we do incorporate friction, then we have a non-conservative force that does work on the system, and it's going to change the total amount of energy that the system has in the end. We can still find the total by incorporating that work done. Okay, so here are some terms that you need to know. Take a few minutes to write these down. Pause the video if you need to. Okay, the next thing we're going to talk about is where an object's total energy is changed with a non-conservative fork doing work. Okay, so we have a couple cases of that happening. The first one, an object ends up with less total energy. So a car is getting to a stop, right? Slowing down, it's losing its total energy, coming to a stop. The work done in that situation by friction is going to take away energy from the system. Our next example is when an object ends up with more total energy, right? I have to add energy to the system. If I throw a ball, right, I'm adding network, I'm increasing the kinetic energy of the system. The next thing we're going to do is talk about a roller coaster situation. So I'm going to talk about a frictionless roller coaster, and I want you to go along with me. Please pay attention to what's going on with the energies without numbers first. Okay. As you can recall, in order to gain potential energy, we have to do work against a conservative force. So from 1 to 2, we are doing work to lift that roller coaster car up to the top of the hill. And you guys know that roller coaster feeling, the click, 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 all the way up that top of that hill. Once you reach that point, you'll notice that that is the tallest point of the entire roller coaster. The car will never go taller than that point, okay? That's where we gain the total energy of the system for the rest of the ride. In our case, we're going to deal with a frictionless roller coaster. In real life, that's not possible, and that's not a good thing. We want friction. We use our brakes very often throughout a roller coaster ride, so that way the car doesn't lose control and fling off the track, right? But for our situation, we're just going to deal with absolute no friction, all energy is conserved in each situation, okay? So at the maximum height, all of my energy is potential. I haven't started moving yet, right? At that maximum height, we pause right before we start going down the hill. So at the maximum height, my velocity is 0, so my kinetic energy is 0. Then once I start moving down the hill, my potential is going to decrease because my height is decreasing. Well, where does that energy go? It's going to go into kinetic energy. And that should make sense because now I'm speeding up, my velocity is increasing, so therefore my kinetic energy is increasing. Remember, when we go with gravity in the same direction, it's going to be positive work done. Once we reach position 3, you'll notice that we are not at a height of 0. We are 30 meters above the ground. So therefore, we have not lost all of our potential. We have both potential and kinetic happening at the same time. We can figure out how much gravitational potential energy we have by multiplying the mass times the g, which is 10, times the height, which is 30, okay? And the mass is given to us in the paper below. We're not going to do numbers yet. We're going to get to that in a minute. So as we go from 3 to 4, right, we're going back up the hill. Going up the hill means we're going to increase our potential energy and decrease our kinetic, right? Our height is increasing and our speed is decreasing. Remember, when we're going against gravity, we have negative work done. That's negative Fg. From 4 to 5, right, at the top of 4, we have both potential and kinetic still. That didn't change. But now, as we go back down the hill, our potential is decreasing. Our kinetic is increasing, right? Our height is going down. Our speed is going up. We're going with gravity, so our work is positive. And we're going down to the 0 level. Once we reach the 0 level, all of our energy is now kinetic. This is our maximum speed location. Okay, at position 2, that's our maximum height. At position 5, that's our maximum speed. Now, obviously, we're not going to stop there at 5, right? We don't just come to a dead stop. We will then continue on along a straightaway where the brakes can kick in and we have friction and our roller coaster will come to a stop. What a thrilling ride, right? Now you're going to go on a roller coaster and think of things a little differently. I'm sorry for ruining your life, I know. So let's talk about some things mathematically about the roller coaster, okay? So now we can say, okay, I know my mass is 200 kilograms. What can I do with that? Well, I know if I have heights, I can find how much potential energy. I know if I have the speed, then I can find how much kinetic energy. In this roller coaster, we have heights. So we're going to start off by finding how much potential at each location. So 200 times 10 times 120 will give us our potential at number 2. 200 times 10 times 30 will give us our potential at 3. 200 times 10 times 80 will give us our potential at 4. Once we have all of that done, then we can plug that in to our table below. Okay, so we have all of our potentials. Pause if you need to write it down. Now we're going to fill in the table. Remember, at the maximum height, all of our energy is going to be potential gravitational. So I know the total amount of energy is going to be the sum of potential and kinetic. So if all of our energy is potential at location 2 and 0 kinetic energy, that means the total mechanical energy of the system is the same as the potential at location 2. Now you're wondering, why is location 1 0? Because we haven't done any work yet. In order to gain the potential that we need for the ride, we had to do negative work from 1 to 2. That was just a reminder. As you continue through the ride, the total amount of mechanical energy does not change. The total amount will remain 240,000 the whole time. What's going to change is the independent potential and kinetic energies. Okay, so now we're going to go from 2 to 3. We are going down the hill. As it goes down the hill, the potential energy is decreasing, and we calculated the potential energy at 3 to be 60,000. We know that's less than 240,000, so that's decreasing. Remember, where did that other energy go to? It's going to kinetic. So we know if the total is 240, we have 60 of potential. That means we subtract and get how much kinetic we have. And we're going to do that for the rest of the ride. So going from 3 to 4, the total mechanical energy remains 240,000. The potential is now 160. We subtract and we get 80,000 joules of kinetic. At location 5, we know going from 4 to 5, our potential is decreasing again. Now we're going all the way down to the 0 level. So that means our potential is going to be 0. We have no more potential to fall or go down. So that means all of our energy is now converted into kinetic energy. So we have 240,000 joules of kinetic energy. Now we can talk about some different things with respect to the roller coaster. Okay, number 1 says, what caused the cart to gain total mechanical energy when going from location 1 to 2? Remember, we had to do work against a conservative force in order to gain potential. Why didn't the total mechanical energy change for the rest of the ride? Okay, because we have no friction and we're conserving all of our mechanical energy. Next question says, how much work was done by the gravitational force when going from 2 to 3, from 3 to 4, and then from 4 to 5? Okay, remember, work done is going to be positive or negative depending on if it's going with gravity or against gravity. So from 2 to 3, we're going downhill. The work is going to be positive. From 3 to 4, we're going uphill, so it's going to be negative. And then from 4 to 5, we're going downhill again, so it's going to be positive. Now we talked about the relationship between the net work done and the change in kinetic energy. So is there going to be net work done by the gravitational force in this situation? Yes, because the kinetic energy is changing. We can determine how much work is done in each situation by finding the change in kinetic energy. So from 2 to 3, if you look at your table, it's going from 0 to 180. So that means there's positive 180,000 joules of work done. From 3 to 4, you have a decrease in kinetic energy, so it's going to be negative 100,000 joules of work done. And then you're going to have an increase in kinetic energy from 4 to 5 of 160,000 joules. So don't forget about your important relationship between the work done and the change in kinetic energy. That will help you understand which way it should be going, whether it's positive or negative. Okay, what effect did this work have on the cart in each of these cases? So if you said that it's increasing kinetic energy from 2 to 3, yes, absolutely. You could say that it's also decreasing potential. From 3 to 4, the work done is increasing the potential. And then the work done from 4 to 5 is increasing the kinetic. Okay, what I actually care about, what you should be looking at is what's increasing in these situations. What is the work affecting positively? Okay. The last part is a little bit more work, pun intended. So once we get to the bottom of the roller coaster, right, the height level is 0, we know we're not stopped yet. That's our maximum speed. We don't want to crash at the end of the roller coaster, so we're going to have to use friction to get the cart to stop. We can figure out that information based on our relationship of work and the change in kinetic energy. But we can also use it with knowing how much mechanical energy we have and figure out how much work needs to be done to get to a 0. Okay, there's different ways to approach it. So if I start with 240,000 joules of energy, and I know I need to end up with 0 joules of energy, and I want to figure out how far the cart is going to travel in order to come to a stop. Okay, this is what we're doing. So I know the end has to be 0 joules. I started with 240,000 joules. Friction is doing the work, and friction is mu Fn. Remember, the work done is opposite the direction of motion, so it's negative. And we're looking for delta X. Okay, if you forgot the work equation, go back and review your last packet. Work done is the force times the displacement. In this case, our force is friction. Friction does negative work. So plug in our numbers, simplify, and then divide. The last part, what happens to the work done by the frictional force which stops the cart? The energy of the system is going to be lost as heat and sound to the surroundings. Make sure you pause at any point during this So that way you have all of the information.